different types of technology and team-based learning affects overall student learning, because Top Hat and CBLs were not always a part of this course. So one of the things I'm going to start doing is I'm going to collect some data and do a little bit of analysis to understand a little bit about the differences in overall student performance, overall student perceptions, on the use of digital teaching interfaces and team-based learning within the large lecture biomedical courses. None of the data is going to be analyzed until final grades are in, and I'm not actually going to see names associated with any of the data that I get back. So what is actually being passed around is a consent form. It is entirely up to you if you want to participate or not. You don't have to. It's really just going to be overall averages of team-based learning grades, exam performance, and a survey that I would send out for people to answer if you agree to participate. All the data that I have in my regular spreadsheet will be anonymized, then it will be sent to Corey. So he won't see anybody's names associated with their grades. I will anonymize it first, and he's going to rearrange everything and anonymize it again so that when I get it back, I have no idea whose grades are. Okay, so that way everybody's data is going to be completely anonymous in terms of how I'm actually going to do this. Okay, so that's what's coming around. You don't have to participate. I would obviously very much appreciate it if you did. But if you decide not to, that's how I'm going to set up the spreadsheet that I send to him to be anonymized, so that only the people who have signed the consent form will be included, will have their data included. And they will also be the only ones that have responded to the actual survey when I sent that later on. Anybody have any questions? Okay. Alrighty. So let's get back to our non-functioning projector system here. If at least you can see it on here. I hope it's not glare. I'm sure there will be. But let's give it a try. Yeah, a little bit of glare. All right. Unfortunately, this is the best I can do until this starts working. All right, so the last thing that we left off at was talking about our PV loop. Okay, and we were talking about the PV loop. We walked through exactly what's happening at each point. How did we come up with the PV loop? Where did we get all the information, the data points to actually make this loop? Yes, that Wigger's diagram or the cardiac cycle diagram that we saw before, that really massive one, that is basically the same thing here. The difference is, instead of looking at how pressure changes over a time course and how volume changes over a time course, we're looking at how pressure changes in response to different points in volume. So starting at point A, we have the lowest volume on the x-axis and also the lowest pressure. Okay, so what state is the ventricular muscle in right now? Contracted or relaxed? Down at point A. Relaxed, right? You are completely relaxed. Everything is at its lowest point. Lowest amount. Oh, sorry, that's just one sleep. Lowest amount of pressure and lowest amount of volume. So, what happens at that point as you are beginning to start allowing volume to increase from point A to point B? What happens at point A?
Mitral valve load opens.
Valve is going to open. Which one? Atrioventricular or semilunar? Atrioventricular. Okay, in this case, we're looking at the left ventricle, so we're talking about the mitral valve. So the mitral valve is going to open at point A, and you have that rapid filling from A to B, followed by the reduced filling from B to C. What is happening in this little lip right here? That bulge is a bulge in, well, this is looking at that little bit of pressure, but that blip in pressure for that final increase in corresponds to what part of the cardiac cycle?
Atrial contraction.
Atrial contraction. Okay, so you're finishing filling it up. At point C, you have now hit that point where ventricular pressure is higher than atrial pressure. You filled it up, enough pressure is generated that your mitral valve is going to close, and now you start systoling. Okay? Same exact volume, no change in volume. The only thing that's happening from C is that you are going up in pressure. That's your isovolumetric contraction, followed by what happening at point D? Yes. Okay. So if you're going to eject, that's starting at point D. What has to happen? Aortic valve has to open, right? So your semilunar valve is opening up, which means your blood inside all of that pressure now has a way to get out. So you have a rapid decrease in overall volume. You lose 2/3 of it in that B portion. And you will have a slight increase in pressure. Why does that happen? There'll be a little bit more pressure on the walls because you're going from a big cavern to a little hole. Okay, it's like going from an underground cave through a tunnel to get out. You're going to generate a little bit more pressure as you are continuing to compress that blood. You're squeezing it even harder. Your contraction of those ventricular muscle cells is going to increase, and you're forcing out that volume. So you're going to have an increase in pressure and a decrease in volume. When you get from E to F, you start to see a drop off in pressure because you're almost at the baseline of your volume. You're almost done ejecting blood. Point F, what's happening there? Aortic valve closes. Okay, why? Pressure is less than what? Less where? Where is this lower? In the ventricle compared to the aorta. Okay, remember that the aorta is going to hold on to a little bit of blood on the other side of that wall. So you're still going to have a much higher pressure. And once the ventricular pressure drops below the aortic pressure, the aortic valve is going to close. And now you're going to start the isovolumetric. Okay? And then that will bring us back down to so I'm it shows them. This is the website. Okay. It'll show. All right. So this is yeah. Just like that's fine. Okay, so here I want to do a quick run through of preload versus afterload. Those of you that did 503 should recognize this figure, but now we're going to talk about it in the context of cardiac. So, what, by definition, what point in that PD loop is going to be resting? Complete resting. No tension or anything on your cardiac muscle wall. Right before you start filling. Okay? Remember when you talk about tension that's developed by a muscle, it can be because of contraction, but it can also be because it's being stretched. Okay? So at resting, which is number A here, it's also point A on that PD loop. It's that point just before your mitral valve opens up. Your ventricular muscle is completely relaxed and it's not being stretched. Right? B is talking about when the preload has been added. Okay? When we're talking about preload specifically refers to a weight that is because that muscle is at rest, so it's not actively contracting, but it is being stretched. So at what point on your PD loop would that be? Right? You're not contracting yet, but you're completely stretched. So right before you start to get any kind of systole, you have everything filling up the ventricle. It's at its maximum point. Yeah. And I'll talk about afterload in just a second. But your preload is right at the end of ventricular filling. The next one on that figure is preload plus afterload, but both of those weights are still resting on the platform. Right, so at this point, we're looking at, so it's starting to contract, and so at what point do we have any adding of the afterload without any additional stretch? We've already stretched the maximum when we looked at the preload. Your preload is your end diastolic volume. It's the maximum amount that you can stretch that muscle. Now you've started to contract, and you've generated that systole, but you haven't overcome the weight yet. Okay? If you haven't overcome the weight, it's the equivalent of saying you haven't quite picked up whatever it is you're trying to pick up. What is that equivalent in terms of cardiac function? Isovolumetric contraction. And when does this point stop before you get to the second one? Right? Because you haven't quite started ejection. So in this case, lifting of that afterload is equivalent to ejection of that blood. So C on this preload versus afterload figure shows your preload and your afterload. So it's stretched, it's also contracted, but it's still being supported. So you haven't overcome that afterload yet, which means you haven't gotten the pressure high enough to open that aortic valve. So it's just before the aortic valve opens, that's point C. And what is the contracted one? D to F. That's your contraction. You've overcome the afterload. The afterload, by definition, is that pressure that has to be overcome, or that force that has to be overcome in order to get contraction and ejection of that blood. So if you're talking about regular muscle, afterload is the weight that you have to overcome in order to be able to lift that weight. But for cardiac muscle, it's effectively the pressure on the aortic side, right on the other side of the aortic valve. That is the force you have to overcome to get blood out of it. That's your afterload. So your preload is your end diastolic volume. The maximum amount that you're stretched, that's that stretching load force. And the afterload is the force against which you have to contract in order to get blood out. Okay? So, resting. Point A, under the blue. Resting and stretched, point C. Contracted and stretched, point D. It's right at D, right before you open that valve, because you are at your contracted state and your stretched state. And then all the way to F, after you overcome and are able to eject that blood, it's the span of that systolic ejection. Okay? Okay, we're going to have to continue this. Apparently, there's a piece of equipment on the projection system is broken, so they're bringing that in. So, see okay. Can you see okay? Oh, you can see. Okay, thank you. I saw hands up and I didn't see the thumbs up. So. Okay, all right. So what happens to PV loop if you're looking at left ventricular heart failure?
Can't grow it any longer.
First of all, if we're looking at left ventricular heart failure, the left side of your heart is not functioning at its full capacity. It's starting to fail, which means it can't generate the same force of contraction. That's called a loss of inotropy. So that word will be up on there a little bit later. But when you lose, I guess it does right now, loss of inotropy on the right. If you lose that contractile force, what does that mean for the blood that's in the left ventricle trying to get to the body? You have more of it staying inside the ventricle. You can't eject as much. That's what's happening on the right-hand side. Quick recap. Over here on the left, this is your standard PV loop in a normal heart. This is your end systolic pressure volume relationship, which by definition is what? Anybody remember? So yes, in a manner of speaking, it is. It's the maximum pressure that's generated that the heart is capable of generating at any given volume. So at any volume value, this is the maximum pressure that this heart can generate. Okay? Your end diastolic pressure volume relationship shows you how capable it is of being stretched. At some point, it's going to curve up and then it's going to stop because you actually can't physically fit any more blood into that chamber. Okay? SD, anybody know what SD stands for? Stroke volume. Okay? If EDV on the right is your end diastolic volume. If EDV is your end diastolic volume. If EDV is your end diastolic volume, and your ESD is your end systolic volume, at the end of diastole, you are maximally filled. At the end of systole, you are as empty as you're going to be. Okay? So by definition, EDV minus ESD is going to be the stroke volume. Okay? That means for every single heartbeat, this SD here is the volume of blood that is going to be ejected from the vent. So when we're looking on the right, the yellow loop is your control loop. That's basically what's going on in the normal heart. The red heart is showing what's happening in left ventricular heart failure. The biggest point here is the change in this ESPR, end systolic pressure volume relationship. What do you notice about the slope? Why is it? You can't generate contractile force, you can't ramp up the pressure to the same level as the heart. For every single volume point, a lower pressure is capable of being generated. You can't get higher than that. Because that ESPVR can never be passed, by definition, it's the maximum pressure that can be generated at a given volume. Your PD loop is never going to go over the top of that line. So if you lose contractile force, so loss of inotropy, causes that slope to decrease, which is going to shift your PD loop. The first part that you've already mentioned is that you have more residual volume after contraction, which by definition is which? What parameter is this? ESD, right? The left side of that red curve, that red loop, that is your end systolic volume. That's the lowest volume that you get under conditions of LV failure. Okay? So instead of what? About 50 mils, now we're looking at 100. If contractile force was the only issue, stop. When you have left ventricular heart failure, your body's going to try and compensate for the fact that it can't get all of that blood out. So what's it going to do? Blood's still coming back. Part of it's going to be, but in terms of the actual muscle itself. What else changed? It's going to stretch to be able to accommodate more. You're also going to have a thickening of that wall as you add more muscle cells trying to increase that contractile. You're going to end up with an enormous. Okay, so your PV loop here is not only shifted over to the right because your end systolic volume is higher. The heart is not capable of pumping out as much blood to get all the way down to what is normal. A compensatory mechanism to try and maintain stroke volume is to allow it to stretch and accommodate more blood. So you end up with a little bit higher end diastolic volume. The problem is that compensatory mechanism is insufficient to meet the change in end systolic volume. So stroke volume in the red here is smaller than the stroke volume in the yellow. Oh, sorry. Okay, you guys see how it's a little bit thinner? So the loss of inotropy is cause for the elevated ESP. The elevated EDV is a compensatory mechanism because the heart is trying to maintain that same level of blood that is bleeding on every single beat. Good? Any questions about this? Oh yeah. No, this is an example. Yeah, this is an example. There are also varying degrees of heart failure, and there's heart failure that can be well maintained. So there are a lot of changes that happen in heart failure, and one of the things that we will talk about is heart failure. Because one of the problems with heart failure is because of that lack of pressure. We'll get to this later in this, but just as a preview. When you can't generate that same amount of pressure, you start to have an increase in overall blood volume, and the kidneys can be used to help generate that excess blood. We'll talk about that when we get to our arrow. But yes, it's going to fluctuate based on the degree and severity of that LV failure, and it will differ. The important thing is to note how your individual patient is progressing compared to their previous. All right. Any other questions about that? Yeah. Yes. Because you have that increase in end-diastolic volume, but because your stroke volume is increasing, the overall fraction of the total amount of blood that's in there is actually being injected. All right. Yeah, this is just to talk a little bit about a little bit of research. Just so good. Great. All right. Thank you very much. All right. So this is one example of how far we've come in different types of research. It used to be when somebody ended up with heart failure, they needed to have a heart transplant. There really wasn't any other kind of treatment that could be done. When your heart stops working, you try to manage the symptoms to restore the ability of the heart. This was published, I think, 2014, in Circulation Research, talking about the long-term effects of adding a gene product, so SERCA2A, by adeno-associated viral vectors. Adeno-associated viral vectors don't cause disease in humans, so they're used frequently to deliver genes that can repair overall function. So for somebody who has different kinds of cardiac events, it has to do with, in this particular condition, it had to do with somebody who has a structurally normal heart. So they're not under conditions of heart failure. They have structurally normal heart that seems to exhibit tachyarrhythmias, so elevated heart arrhythmias under conditions of exercise and stress, even though there isn't anything physically wrong with the heart. One of the benefits of the kinds of research, you're not going to be quizzing, so you don't freak out. Okay? This is just to introduce you guys to the stuff that's constantly happening. There are so many big advancements that can be made that a single dose of this particular, makeup resulted in a drastic drop in overall morbidity and mortality of people with this. And it seemed to be dose dependent. The highest dose, a single shot, protected people for months to a year, but 82% didn't have another cardiac event for the next 3 months, despite having visited hospitals and had other cardiac troubles throughout their daily lives. So the types of stuff that we're going to be talking about, we're going to talk about SERCA in just a little bit. You'll understand a little bit about why that would be really important and able to help maintain overall normal cycling of the function of the heart in terms of heart rate. But the benefits of the kinds of research that's being done is it allows us to be able to do non-invasive types of treatment. The last part I wanted to talk about was I wanted you guys to take a little bit of time to see if you can figure out which change in PV loop you would expect under each of these different conditions. So this one, I'm asking you about increased preload. A, B, or C, which do you think would be what you would expect to find in terms of how it would change if you increase just the preload. Preload only. Contractility, your inotropy stays the same, your afterload stays the same. The only thing that's changing in this instance is your preload. So where does that show up on that? Top one's A.
I think it would be A. So increase preload, that means that you're
that's my guess.
increasing the volume of the heart. That's really the only one where the volume increases.
Yeah. Devin, what do you say?
I think it's A too.
Yeah.
It's a preload. The part the preload supply
Another
is
10 seconds.
equivalent to the C.
You're gonna see
That's
that,
where C is.
that left shift.
I think, yeah.
All right, 3, 2, 1, and we're done. All right, so here's the results we got. All right, we got lots of, everybody picked one of each. All right, so correct answer is anybody that put A. Your preload by definition is your end diastolic volume. So if you increase only the preload without increasing anything else, the only thing that's moved
These questions should come from
is the right side of that leg. So you can't see any of the gray curve on here, but you can see the black line that shows where the end diastolic volume used to be around what 110, 15, and then now it's up to about 100. The end systolic volume. What can you do 503 people? Well, that by definition, you do have the same initial starting point, but how are you able to get from a much bigger end diastolic volume the same end systolic volume? How come your stroke volume? How can that be? Your ejection fraction is going to be increased, right? Ejection fraction is just your stroke volume divided by your end diastolic volume. Fraction of blood that's ejected based on the total amount that the blood can hold, or the heart can hold. So in this case, your ejection fraction's gone up, stroke volume. Nope. In this case, what we're looking at, you've increased your preload. The reason that you can still get down to that end systolic volume is because of something called the Frank-Starling mechanism. Now, just to reiterate, for those of you that did 503, we talked about an optimal length for cross-bridge cycling, optimal overlap of actin and myosin filament in that sarcomere. One thing I also mentioned at the time that I'm going to talk about now, which is today, is that cardiac muscle operates below that optimal. That means that you can elevate the force of contraction if you have to accommodate a greater amount of volume. Frank Starling. Frank-Starling, not his first name. Two last names. Nobody in science ever wants to do that. So, what's actually happening here is normal operating procedures indicate that you actually have a less than optimal overlap of actin and myosin in your cardiac. Okay? So the force that's generated is a little bit lower than is capable of generating. The reason for that is to accommodate the changes in venous return. You will have circumstances that will cause your blood volume to go up. If you have more blood coming back to your heart needs to be able to not only accommodate changes in venous return, changes in the amount of blood that's coming back, but also be able to maintain blood flow. All right, so Frank-Starling mechanism, basically by stretching that muscle cell, each of those sarcomeres are effectively pulling to their maximum overlap. And because of that, they can generate a little bit more contractile.
My volume is increased.
Yes, it is.
So, what, in theory, would the
So, so
is it increasing that preload?
you will have that increase in overall preload because you are circulating a lot more volume. The other thing is, depending on overall, I guess, how far you are in the pregnancy, the volume load will increase. It will also have an effect on your overall heart rate. It'll change as well to accommodate to make sure that you're maintaining circulation, not only to the fetus, but also to health. So you will have that increase in preload, and this system will actually kick in as a result of that extra volume load. But it happens, it won't look exactly the same, but it will have that increase in diastolic volume, and you will have that compensatory increase in contractility to make sure that you're still supplying blood to the rest of the body. Increased volume. But this can also happen under conditions of exercise. So people who exercise heavily, not only will you increase your heart rate, but you can also increase your stroke volume, specifically because you have a greater amount of blood that's coming back per unit time. And when we're talking about all of these, we're looking at changes in volume and changes in pressure, but your heart rate specifically in terms of stroke volume is how much is actually being pumped per unit. So as your blood starts to flow a little faster when you're exercising, you have more coming back, you're going to increase the rate that's returning to the heart. So that would be an example of that preload, but you can also have it under exercise. Stroke volume, heart rate, respiratory heart rate will actually go down because you increase the force of contraction of your heart. You see differences between somebody who's never exercised and somebody who exercises, either like marathon runners. You see differences in terms of the actual stroke volume and diastolic volume because of changes due to activity or inactivity.
And for an athlete, for somebody who's an athlete, a marathon runner, this is sort of a permanent change, and then what happens when they go back to a more sedentary lifestyle, or they're not a marathon runner, their kidneys just filter out.
Yeah, your body's constantly in flux. So if you stop running altogether, you stop exercising altogether for whatever reason, your body will adjust to having that excess blood volume. The other thing is the extra muscles that you've developed in order to increase that contractility, they will eventually thin out too. So you can build muscle and you can lose muscle because your body's recycling basically. All right. Next question. You will find that these questions will get progressively easier because so if you missed the third one, I'm going to be very All right, so now we're looking at increased afterload. Which one of these is going to deal with increased afterload? I'm also going to get mad. Clearly, that's a preload. All right. And pick between B and C. Think about what afterload is. Remember, you're assuming that your preload is held constant and your contractility is held constant. All right, I'm going to stop you. Looks like we're doing pretty well. So, increased afterload. By definition, what is afterload? It's the aortic pressure for our left ventricle. It is the pressure against which you have to overcome in order to get rid of the contents of that chamber. So, pressure on the other side of the aortic valve is what you have to overcome. If you increase that pressure, what do you have to do to get that aortic valve open? You have to increase the pressure inside the left ventricle, right? So basically what we're looking at here is the difference between this point, okay? Because where I drew the line, the bottom one corresponds to the gray curved with the black line. That's the point at which the aortic valve is going to open, which means you've generated sufficient amount of pressure inside the ventricle to overcome that aortic pressure. You can open it up and eject your blood. If you increase the pressure that needs to be overcome, you have to increase the pressure inside the ventricle in order to get that valve open so that blood can be ejected. Have you ever tried to lift up a single sheet of paper, or let's say a stone, like skipping stones? Anybody ever skip stones? Water? Okay. Lighter the stone, easier it is to skip. Okay, you pick up a huge boulder. First of all, you're not going to pick it up half as fast. It's a small pebble, and it's not going to accomplish its goal. This is basically what's happening here. The muscle fiber is capable of contracting and therefore shortening in length at a speed concomitant with the weight it's trying to overcome. Picking up a piece of paper versus picking up this textbook, you can contract faster. The velocity of shortening is faster when you pick up a piece of paper than it is when you pick up a pencil. Same thing here. Because the velocity of the fiber shortening is going to be slower, now that you have a larger pressure on the other side to overcome, your stroke volume is going to be your ejection fraction is going to be because your stroke volume is lower, but the denominator of that equation, the end diastolic volume, is stable. So the fraction of blood that you're ejecting per heartbeat is now less. Under conditions of increased afterload, as long as you're keeping a constant preload, that's here, constant preload and energy. That's important to know. All of these PV changes are taking a look at hypothetically what would happen if we change one of these three. So, sorry, I hit the wrong button. All right. Tell me what you think. What if you dropped in a trophy, but your afterload and your preload stay the same? Oh, good. Thank you. See, nobody is checking anywhere else. That's it. Your preload hasn't changed, so your end diastolic volume hasn't changed. That's what's happening here. That's the same. Okay? Your contractility is the only thing that's changed. You haven't changed your overall afterload, which means that this point is okay. So preload's the same, which is in blue, and that purple line is the afterload, showing that that's the same. The only thing that you've done is you've messed with your ability to generate that strength of contraction. Same preload, same afterload. Contractility goes down, you go play. All right. And as I said before, since you lost inotropy, we're looking very specifically at this. You have lost the ability to generate pressure at any given specific. All right. Any questions on this wrap up of the material from last time? Yes. Go ahead. Okay.
Those lines seem to like be rotating around a fixed point. Is there like a lower particular pressure that's like an absolute minimum that is rotating around the side of the other? Like you see a black line that looks like it rotates when you go to the red line. Is there like a lower left particular pressure below that you go out to the other?
Oh, yeah. So yeah, but so it stops before it ever gets to that wire step because you're never going to be able to eject all of the blood. So you're never actually going to get to that Y intercept because your heart is always going to have some blood. So it will continue down that trajectory. In theory, you could actually vacate all the blood. So we're specifically looking at what's going on inside the chamber itself. When you're talking about the overall change in blood pressure, you're talking about the arterial pressure, and that's what's measured outside. Okay, so when that'll actually come into play when you look at the difference between the stroke volume of the heart and the amount of blood that's actually getting out into, right? It does. It does. Afterload especially. Because afterload by definition is changing the aortic pressure, which is what's more mirrored on the nerve supply. So what I'm saying is that the volumes that are changing here, the stroke volume, by definition, we're assuming that all of that is leaving out the aortic valve. What happens is what if it's leaving the heart before you? Where else? Right? If they have a problem with your mitral valve. And when all that pressure is generated, in theory, you should be able to squeeze all that stroke volume out the aortic valve. But if you have a problem with the mitral valve, it's a pretty common problem with valvular disease. If you get mitral regurgitation, you could squeeze out 75 mils of blood, but let's say 65 mils of that go to circulation and 10 mils of that goes back to the atrium because of the okay? So that kind of stuff will come into play. We're looking specifically at what is happening inside of one particular chamber. All right. Any other questions? Yes.
So is it more, do you see this all kind of together in like the heart tissue, or are they more like isolated? If you just have increased preload or increased preload?
Well, based on what we've talked about before, the first example, they're all going to have a role. They might not every single one of them change, but the body is very resilient and it will compensate for change. That's what we saw with the first one. We saw the LV failure. This, in theory, is the same precipitating factor of LV failure, loss of. But that other figure showed that it actually shifted over to the right. You had the same overall shape, but it shifted to the right because you had a compensatory increase. So yeah, that's why I specified that these figures are showing you just how one particular parameter change will affect the appearance of the loop. But under pathological conditions, you will have either one or more that are changed because of pathology, and then you'll have one or more that is likely changed as part of it. Good question. All right. Okay, so we sort of talked a little bit about this already in terms of properties of cardiac muscle cells, specifically in terms of the length of the sarcomere that cardiac muscles normally function at. This is a figure from the boron book. This one shows, really in the middle, you're looking at your myosin. They have that anti-parallel arrangement, so the heads are at either end. Look kind of like this. And then your actin filaments are going to align anchored at the edges of the sarcomere, anchored at your Z-disc. Z-disc to Z-disc is going to be the length of your sarcomere. This is going to show your optimum overlap. Every single myosin head is in contact with an actin filament. The nebulin and the titin, those are things that we cover in 503. Titin gives it elastic properties. Nebulin helps to anchor it to the Z-disc, helps actin anchor to the Z-disc. Titin helps to anchor the M-band, which is where the myosin cells are anchored. That's 503 territory. But for those of you that did 503, this should be pretty familiar. Cardiac muscle, I think I showed this figure in 503, but I omitted the last column. Now I'm going to show you the last column and show you how it differs from skeletal and smooth muscle. The biggest changes that we're going to look at here is that we have striations. We obviously have actin and myosin because that every single one of these is going to have the actin and myosin. It's under involuntary control. There's intrinsic control and there's extrinsic control. The Frank-Starling mechanism is an example of an intrinsic mechanism. It doesn't need to get a signal from any nerve or any hormone or anything else to change the overall stroke volume of the heart in response to changes in return. It's strictly a property of that cardiac muscle tissue itself. The similarity with striations is for your skeletal, but for most of what you're going to see here, you're going to see a lot of similarities with you have autonomic, right? And you see that in your spoon. That is not something that you would see in your skeletal muscle. You also have varicosities, so the overall structure is a little bit different. The biggest thing that is important to understand with these types is that it's not on my list, but I'm going to point out one other part. Troponin. It has the same troponin and tropomyosin system for regulating calcium that skeletal muscle. The biggest difference is that source of calcium. That source of calcium is similar to spoon. So as you can see, the cardiac muscle is going to be kind of a blend between skeletal and spoon. It uses the same calcium sensing mechanisms that you find in skeletal, but it requires extracellular calcium like spoon. It uses striations that has the sarcomere set up, but it also has these varicosities instead of active neuromuscular junction. All right, so looking at your cardiomyocyte structure, similar to what we see in skeletal muscle in terms of striation, the biggest caveat that we have that's a little different is that we have these things called intercalated discs. So your cardiac cells have that striated function, they have that sarcomere function, but they function as a physician. They're capable of contracting all at the same time, which I don't think is what we want, right? We don't want your heart to have every single muscle fiber stimulated individually, which is what we see in skeleton, right? Intercalated discs have very low resistance in between them. They are effectively gap junctions that electrically couple neighboring cells. Same thing that you would see in unitary smooth muscle. So unitary smooth muscle means smooth muscle capable of functioning as a unit. Electrical coupling of those cells, those neighboring muscle fibers, means that when one is stimulated, the electrical current inside of that cell passes directly into the neighboring cell. They can all get the stimulus to contract together, even if those neighboring cells did not directly receive that electrical stimulus. All right. Quick question about another feature of cardiac muscle altogether that makes it different. About the fact that top factory is the word answer. That's the word, that's the way that types it, then you'll get it wrong. Answer that question. That's why I don't write. I'm going to stop here. Let's see what we have here. ATP, mitochondria. Nice rolling. Lots of single-printed mitochondria. This one, that is full. So, if you're going to get muscle contraction, you need not only do you need to have lots of mitochondria, because you need lots of ATP. You cannot get contraction of muscle. Cross cycling, you don't have ATP. ATP is required to progress through the entire cycling, cross-bridge cycling process. Without ATP and the hydrolysis of ATP, you don't get contraction. Right? So you need a lot of ATP. You have a lot of mitochondria. Why does it also need to be highly vascularized? We're talking the equivalent of about 1 capillary per muscle. A lot of vascular. Lots of nutrients, lots of oxygen. Why? Right? If you want aerobic respiration to generate all that ATP, you better supply it with sufficient amounts of oxygen to be able to run oxidative health. Okay? So, if you want the heart to continue to contract over the course of your lifetime and have that lifetime last for decades, lots of vascularization, lots of mitochondria. And the vascular tissue is there to feed mitochondria to get enough ATP so you can have constant contraction. Not like the heart with a break. It does get a break, but it's kind of a that's it. Okay. Cardiomyocyte structure. This on the figure A actually shows what it would look like if you had HB staining, just to take a look at actual muscle fiber under a microscope. And then B is really showing a little bit about what is happening in between each muscle fiber. So there are two things that I want to point out here. Two things I want to point out. We have percolated disc, and we have desmosome. All right, the biggest difference here is that they're both going to be present. This is the desmosome right there, and this is the intercalated disc. The intercalated disc, as I said before, that's for electrical coupling. That means that your neighboring cardiac myocytes, so the cardiomyocytes is just heart muscle cells. Cardiomyocytes are electrically coupled with their neighbors, so that if you depolarize one, that depolarization will spread to every other muscle cell that is. Okay? That's a good thing, so that you get all of the atrial cells to contract at the same time, and then all of the ventricular cells. The desmosomes are mechanical. These, anybody take cell biology? Talk anything about like how you mechanically create tissue and you link them together, intermediate filaments? We talked a little bit about it in 503. Desmosomes are the points for mechanical coupling between neighboring cells. It's so that if we're dealing with an organ that is going to be excessively stressed repeatedly, there needs to be something other than just a gap junction really between the neighboring cells to hold them together. Your desmosomes are there to mechanically provide support to link neighboring cells together so that all of that stretching doesn't rip your cells apart and cause them to no longer function. That's another thing that's different from the skeleton. So even though striations are the same, the calcium sensing mechanism is the same, the overall structure, the intercalated disc, will allow for electrical coupling, the varicosities, and the fact that extracellular calcium is necessary for the heart to function are more akin to sleep. So it's sort of a blending. You're not tested on skeletal. I'm just making relations because even if you haven't taken 503, you've probably been at least introduced to different types of muscle in the body. So it's more for frame of reference. I'm not going to test you specifically on, compare skeletal and cardiac, compare smooth and cardiac. But you should know the specifics for cardiac, which is troponin and tropomyosin regulate calcium. Extracellular calcium is required. they're electrically coupled by intercalated discs, the desmosomes. So any of the things I specifically said for cardiac is fair game, but I'm not going to actually start. All right, this one is just a close-up look. I think it's also from the boron book, but it gives you a little bit of a closer view of what's happening in that intercalated disc. Specifically, that your gap junctions, that's for electrically coupling, right? And your desmosomes, mechanically coupling. Right? Any questions on the function of these and the overall appearance of cardiac? Now we're going to look at the ventricular muscle action potential. We will be looking at the other action potentials, but that will come on Thursday. Right now, we're just looking at ventricular action potential, or action, yeah, ventricular muscle action potential. We have our 5 different phases, and different channels are going to be responsible for the changes in membrane voltage that you see at each one of these phases. The first thing that's going to happen, typically you're hovering around -85 to -95. That would be your resting membrane for cardiac. More negative than the -70 that you kind of use as sort of a catch-all for most cells. Different types of cells with different functions are going to have varying resting membrane potentials based on what their overall intention is. In this case, we're looking at about -90. And in order to get that rapid depolarization, it's about 105 millivolts that you're going to see from about that the section of -85 up to about +20 in this figure. That's 105 millivolt change during that depolarization part. So the peak is going to come all the way up to +20. So on the y-axis, we're looking at the voltage itself in millivolts, and on the x-axis, we're looking at seconds. We're looking at, okay? First thing that happens, which is phase 0, that is the opening of your fast sodium channel. This is specific for ventricular, not for all heart cells. Different types of heart cells that have different types of action. This is specific for ventricular. Fast voltage phase sodium channels are going to open, and then you will also have an opening of your L-type calcium. L-type calcium channels open a little bit more slowly. Just the kinetics of opening and closing is a little bit more slowly. And they, by that depolarization, will be triggered to open as well during that upshoot. You see a little bit of a dip once you hit that peak, and that's because your potassium channels have now started to open. They're also voltage. And the kinetics are a little bit slower for causing them to open and close. But when your potassium channels open, because you have a lot of potassium inside the cell and not so much outside the cell, the gradient will be for potassium to leave the cell. Sodium has a much higher concentration, so does calcium outside the cell. So it's going to enter. That's why when you open those channels, the entering positive charges will cause depolarization. This slight repolarization is because as soon as those potassium channels start to open up, you still have calcium coming in, but now you have potassium. Okay? And that initial opening, I guess, takes the balance a little bit. This plateau is because those calcium channels are now in full force. Potassium channels are also open, so you have positive charges coming in by way of calcium, you have positive charges leaving by way of potassium. Your sodium channels are closed. They open fast, they inactivate, flow of sodium is done on that upstream. Okay? At this point, you have calcium coming in and potassium coming in. So the voltage itself is going to roughly plateau, relatively constant during that point. As the calcium channels begin to close and get more of the potassium channels opening, you're going to start seeing less calcium coming in and a constant efflux of potassium. going to be the repolarization side to allow resting membrane potential to come back down. Your action potential voltage to come back down toward resting. The other thing that will happen is as those channels are starting to close, your potassium channels, once you drop below a certain voltage, they're going to close because it's the voltage trigger that causes them to open. So when you get below that trigger, that threshold, the current close. There are G protein coupled rectifying potassium channels and PIRK. Those help to maintain overall resting. By definition, an inwardly rectifying means that potassium specifically flows into the cell. It cannot flow out of that. Anytime we're talking about channels, the direction of flow is solely dictated by electrical gradient and chemical gradient. Unless you're looking at a rectifying channel, which has a specific direction. That helps to kind of stabilize as the rest of those potassium channels are closing, to get you back down to that resting membrane potential, which is at 0.4. So if you want to look at it from a figure standpoint, this one came from the Barnum Levy. At 0, we see fast sodium channels, fast voltage gain sodium channels that are going to open and inactivate rapidly. They're responsible for that upswing. The ITO, the I is for current, right? So back to IR, that little I, that TO stands for transient outward. Okay, that actually has to do more with your P-type calcium channels versus your L-type. L-type calcium channels are doing run the work here. You get a transient outward current that is going to show for potassium channels opening up. You get a slight repolarization, and then you have 3 different types of potassium channels that are all working to balance out the calcium that's coming in. Phase 3. Close those calcium channels now when you're beginning that repolarization point, and potassium channels are responsible for maintaining that resting voltage. You will have a slight fluctuations in the way that these currents are happening because you have multiple different types of potassium channels, different types of calcium channels, all of which have slightly different kinetics. Okay, so each one of these, the ITO, IK, IK1, all of these are different types of potassium currents. They're all under the global heading of voltage-gated potassium channels, but there are like 7 different. So we're just going to talk about, it's not a cell class, but we're just going to focus on the group as a whole right now. But it is important that you understand that these different potassium currents are due to different types of potassium channels, all of which function to allow potassium to move across the membrane. They're voltage-gated, but they activate and inactivate it. All right, this figure here, I think I gave you this one ahead of time. Another question, right? The reason for that is because we did just talk about the action potential itself, but we haven't talked about what's happening underneath. So what are we looking at down below? Current, right? These are all currents. We have sodium, calcium, and we have potassium. Which direction, above or below that dashed line, tells you that current is moving into the cell? Okay? This means where it's below, that's in. Okay? If you are above, that's out. This is a standard readout. Whenever you're looking at current, if you're doing a patch clamp experiment and you're looking at current, any movement below that baseline shows that you have current flowing into the cell. Anything above that dashed line, which is that baseline, shows that you have current moving out of the cell. So you'll see the timing here gives you a little bit more of an indication of what's actually happening schematically. And in terms of its time course, over the the 200 to 300 milliseconds of that action, well, of the plateau. Typically, your action potential in my cardiac muscle can be anywhere from 250 to 400 or 500 milliseconds. And that's actually going to become very important in why your heart rate is dead. So, what's the first current? What's the first ion to flow? Sodium. It's quick. It's very quick. It opens, sodium comes in, it inactivates, sodium current's done, and the rest of it, nothing. No more sodium current after that initial cluster. Okay? Depolarization because of sodium coming in. Now, if sodium's the first one, what does that mean for the voltage, the threshold at which it's activated? The first one to activate. So, sodium is going to activate first. Your calcium and your potassium are both going to be activated by that depolarization, but they're going to happen at a slightly different rate. So calcium is going to follow this, I'll erase it in a second, but it's going to follow this trajectory where it comes in and then they start to close, right? And then it stays steady for the rest of the time. Okay, so you have the opening here, but this is closed. Okay? They started to shut, you no longer have it coming in. You've reached that baseline, no more calcium is playing any kind of role. That's why you see this, that plateau. It corresponds with what's happening with calcium. When you look at potassium, you see that it starts and it continues to stay elevated until after you've gotten down to that repolarization, when they finally start closing. These don't inactivate. Once they're open, they stay open and allow ions to flow until the overall voltage drops below its threshold. Right? So your potassium is partly responsible for this plateau, and it is certainly responsible for the repolarization.
For phase 4, you said that it says on that picture that sodium was coming in and out on the previous slide.
0. That's phase 0. Phase 4 is the resting. Here. Big.
On the next slide, though, it's got like a channel of sodium coming in and out.
For phase 0.
For phase 4.
Oh, yeah, that's supposed to be. So you will, so I should say that you actually have both of these. You want to get technical? I should, because this figure is a little messy. I didn't want to confuse you, but you do have channels that'll have something. Talk about that in private. You have some ions that are capable of leaking across even at baseline voltages, but that balance is maintained. You don't have any net movement, no net current moving, because that balance is going to be maintained with a sodium potassium pump that is constantly working. Any leakage of sodium coming in and potassium leaking out is going to be pumped back out for sodium and pumped back in for potassium. So when we're looking at specifically the resting membrane potential, then we're talking mostly about like a net, you have a net flux of that potassium that is responsible for. That means there's no net current. Yeah, it doesn't mean that there's no current flow, because you will have some moving in both directions. It means you don't have a net. In this case, this is only measuring from that baseline that you could have just equal amounts moving in and out against each other. It's when you have a net current moving in or a net current moving out that it starts to show up. Because calcium coming in and potassium. And that's actually this section here. See that they're both open right here. They're both open until you see that you're starting to lose that calcium and then potassium. the reason that it comes back down and it sort of stays is because you still have your potassium channels that are allowing a constant leakage of potassium out of the cell, which means that it stays negative. You're always losing positive charges. But you have these inwardly rectifying potassium channels that also allow potassium selectively to come into the cell. And that's why it tends to stabilize and doesn't move. So the last part I wanted to talk about here is just an overlap of what we're leading into next. On the top, you have the ECG for the ventricle. So it doesn't show the P wave, but the atrium. In the middle, that shows the action potential that's at the top on the left. And the bottom is what I'm going to lead into next time. This is for tension. That's the mechanical response, how the muscle responds to the electrical changes in the ventricle. All right, that'll do it, and I will see you guys on Thursday.